Alright folks, back with another video here. We're going to check out the concept of confidence intervals for two proportions. In a previous lecture, we went over the confidence interval for a one sample proportion. In this case, we're going to go over two samples. So sometimes we want to be able to compare the difference between two population proportions. So we're comparing the proportions of two different groups. For example, let's say we were interested in comparing the proportion of men that earn $100,000 salary versus the proportion of women that earn $100,000 in salary. In order to do that, what we do is we collect two different samples and we're going to calculate a confidence interval for the difference between those two population proportions, which will be P1 minus P2. This process that we will go over in just a second is called the two proportion Z interval. Okay? So before we get into how we perform the two proportion Z interval, let's go over some conditions. And the bulk of these conditions should seem very familiar. It's just that we have one new extra condition here, is the independent groups assumption. So remember, now we are comparing two different groups. So we need to make sure that those two groups are independent of each other. Okay, meaning one group's results has nothing to do with another group's results. All right. Even if we're not told that they're explicitly independent, all we need to make sure is that it's reasonable to assume that the groups are independent. For example, in the example that I gave you guys at the beginning here, we're comparing the proportion of men that make 100K versus the proportion of women that make 100K. We can reasonably assume that those groups will be independent there, okay? Even though I didn't say that they are independent. So we need independence between the groups. And we also need, this is getting back to the condition that we're more familiar with, we need independence within the group, right? We need that independence assumption, and we're very familiar with it. We know that there's two kind of ways, two touch points, and for us to touch on independence within a group. Randomization. If we collect the data randomly, that's going to help us with that independence assumption. And once again, even before, like what we talked about before, even if we are not explicitly told that the data was collected randomly, we only have to check that it's reasonable to assume randomness. Okay? All we need to make sure is that it's reasonable. And then another part of the independence assumption is that we need to make sure that we sample less than 10% of the population. All right? So we have those. So we have independent groups. We have the randomization condition. We have less than 10% of the population sample. And then, as you guys hopefully know, for proportions, we have to ensure that we have the correct number of successes and failures, which we often refer to as the success and failure condition. Well, usually what we do is we do n times p and n times 1 minus p. So you may be asking yourself, why do I have four kind of checks here? Well, remember, we are taking two different samples. So N1, maybe we should write out some of this. N1 is the sample size, is the sample one size, right? And then N2 is going to represent the sample two size. All right, and then remember P hat, so P1 hat is the sample one proportion of success, and then P2 hat is the sample two proportion. So what we're saying is we need N1 times P1 to be greater than or equal to 10. Remember, when we take N1 times P1, that gives us the number of successes. We need N1 times 1 minus P1 to be bigger than 10. We need the number of failures. So we're checking the number of successes and failures for each of the samples. N2 times P2, that gives us the number of successes. N2 times 1 minus P2 gives us the number of failures. And so that will give us, we need all of those to be greater than or equal to 10. Okay, if all of these conditions are satisfied, let's take it back from the top. We need independent groups. We need independence within the groups, and we check that by looking at the randomization condition, and we also check the less than 10%. And then we have the success and failure condition. If all of those are true, then we are going to be able to calculate the two proportion Z interval. Okay? And so what's the two proportion Z interval? So we start off with taking P1 hat minus P2 hat, right? That's the center of our interval. All right, that's called a point estimate. So we take that, and then we're going to add and subtract the margin of error. Okay, and so this margin of error, I'm not going to lie to you, is a nasty little formula. So what you do is you take Z star. Remember, Z star is our critical Z-score. And we multiply it by the standard error. So let me see if I can highlight everything that I'm about to, let me see if I can box this up. This part right here is our standard error. Okay? And like I said, it's a nasty one. You take the square root of your P hat, P1 hat times 1 minus P1 hat over N1 plus, and you do the same thing for P2. So, I mean, really, it's not that bad. We're doing really what we did with the one proportion Z interval. It's just that we're adding on that extra part for the second sample. Okay. Once again, before we jump into some examples here, actually I have just one example. Let's remind ourselves what are some of the interpretations of a confidence interval. Okay. So recall what it means to be 95% confident. 95% confident means that in 95% of all confidence intervals that are created from random samples of the population, they will actually contain the true difference in those population proportions. We do not know what that value is, but we're saying that this method is basically correct 95% of the time. Remember, each sample is going to generate a different confidence interval. But something that's new, since we're comparing two different proportions here, let's take a look at these different scenarios that could happen. So remember, we're doing P1 minus P2, right? So if you do your confidence interval, and it turns out that it contains all negative values, what does that mean? That means that our confidence interval is saying that P1 minus P2 is less than 0. That's what it means to be negative. If I solve that inequality, if I add P2 to both sides, this means that we are confident that P1 is less than P2. So that's the connection there. We are saying if we get all negative values in our confidence interval, we're saying that we are confident that P1 is less than P2. The flip of that, if we get all positive values in this confidence interval, we're saying that P1 minus P2 is greater than 0, which means that we are confident that P1 is greater than P2. That's the difference. Okay, so if you get all negative values, you're saying that P1 is less than P2. If you get all positive values in your confidence interval, you're getting P1 is greater than P2. And then if you get in the scenario where you get both positive and negative values in the confidence interval, then we really cannot make a statement about one proportion being higher than the other. Okay, so we can only really make a strong statement if we have all negative values or all positive values. Okay, enough being said, here we go. For example, COVID-19 outbreak resulted in mass closure of businesses such as restaurants all across the U.S. A Pew Research survey conducted in April 2020 asked whether respondents had ordered groceries online as a result of the pandemic. 23% of 2,698 randomly sampled college-educated adult respondents answered affirmatively, so they did order groceries online. This is compared to 19% of 696 randomly sampled adult respondents without a college education who responded affirmatively. Okay, here we go. Part A. Are the conditions met in order to perform a confidence interval for the difference between the population proportions? All right, so recall, what is our kind of first condition we should check? We are going to check if we have independent groups. Okay. Well, they don't tell us explicitly that these groups are independent, but it's reasonable to assume independence. Okay? Why is that? Because remember, independence means one group really doesn't influence the other, right? And so we're talking about two different groups of people. We're talking about college-educated people versus non-college-educated people, right? And so there's really no dependency. There's really no relationship between the two. All right. So it's reasonable to assume independence there between the two groups. What one group does doesn't affect the other group. All right. What else do we check? Now we need to check for independence within the group, right? And so one way that we check that is we look for randomization. And they tell us this data was collected randomly, right? So we have randomization. And even if they didn't tell us this was randomly sampled, we can once again still, it's reasonable to assume that the samples will be random enough. Okay? All right, also, we have our less than 10% condition. Certainly, we only sampled 2,698 college-educated adults, and we only sampled 696 non-college educated adults. So yes, we have less than 10% sampled. And lastly, we need to check our success and failure condition. Success and failure, okay? All right, so in order to do that, we need to grab some information. So first of all, let's talk about P1 hat, okay? What we're going to do here is let's let 1 represent the college-educated adults, and let's let 2 represent non-college educated adults. Okay? All right, so P1 is going to be, let's see, what percentage of all college, or what percentage in the sample or college educated that order groceries online? 23%. So P1 hat is 0.23, which means N1 is at 2698. So we're just grabbing all this information. Okay, and then we have P hat 2, or P2 hat, I should say. I don't know if you guys can see that. P2 hat will be 19%. So 0.19, and N2 was the 696. Okay, so let's raise this up so you guys get a good view here. 696. So what we need to check is, do we have more than 10 successes and failures? And we can certainly see that's going to be the case here, right? So what we'll do is we'll do N1 times P1 hat. Let me do a different color here. All right, so we're going to take 2698 times 0.23. 0.23. And we get 620.54. I'm just going to round that up. Just round up to the nearest whole number. So that's approximately 621. All right. Remember, this is the number of successes. All right. We're also going to check the number of failures, which would be N1 times 1 minus P1 hat. Let's see what that gives us. So that will be 2698 times parentheses 1 minus 0.23. And this is the number of failures, which is 2077.4. Let's just round up. 2078. All right, so there we go. So both of those are greater than 10. So far, so good. Now we do the same thing with sample 2. N2 times P2 hat. So that will be a 0.19 times 696. That's 132.24. I'm just going to make it 133. And then we're going to do N2 times 1 minus P2 hat. And that will be the 696 times 1 minus 0.19. I know I flipped my order of multiplication, but the order of multiplication never matters. And we get 564, let's call it. I'm just always going to round up these numbers. All of these are bigger than 10. We are good to go. All right, remember the success failure conditions that we need them to be greater than 10. All right. Successes, failures, all over the place. So hopefully you guys understand that. So we have all the conditions met. So can we perform a confidence interval? Yes, we can. All right, let's keep it moving. Calculate the standard error for the difference between population proportions. Okay. Remember the standard error, if we go back, that was part of our margin of error. The standard error was that thing, right? It was the square root of P1 hat times 1 minus P1, so on and so forth. So let's just copy down that formula here. All right, so the standard error, we'll call it SC, equals the square root P1 hat times 1 minus P1 hat over n plus, and all of this is underneath the square root. We do the same thing with P2 hat. Over n2, this should be n1. That is our standard error, okay? All right, all we have to do now is fill in our information. So the standard error equals the square root of P1 hat was a 0.23. And let me say this really quickly, guys. P1 hat, so in this particular question, they gave us P1 hat already. But if you guys recall from previous lectures, to get P1 hat, all you do is you take the number of successes, right? And you divide it by your sample size. In this case, sample 1 size. And you do the same thing with 2. So instead, if they had told us, out of 2,698 college-educated adults, 621 of them order groceries online, I would take 621 divided by 2698. That's how I get my P1 hat. So I want to make sure you guys are clear on how you can get your P1 hat if it's not given to you, okay? But for us, we're lucky. P1 hat is given to us. It's a 0.23. So we take 0.23 times 1 minus 0.23, and we divide that by our sample size of, I believe it was 2698. Yes, 2698. Plus, now we do P2 hat. P2 hat was 0.19 times 1 minus 0.19. Divide that by the sample size was 696, I believe. And now we put this monstrosity into the calculator. Let me show you how to do that. Spoiler alert, I'm going to show you how to do this using technology, which will greatly simplify, or excuse me, it'll speed up this process. So just hang in there. All right, let's go to our calculator. Let's clear this out. Start off with the square root. We do 0.23, open parentheses, which indicates multiplication, 1 minus 0.23. Close up parentheses, still staying within my square root. Divide that by 2698. The calculator will do the correct order of operations, still under your square root, plus. Now we do, I believe it was 0.19 times 1 minus 0.19. Divide that by 696. That looks good. Get out of that. Let's calculate it. To 3 decimal places. Let's go 3 decimal places. It's a 0.017. So that is our standard error. All right, moving along. Calculate the 95% confidence interval for the difference between the population proportions. So I'm just going to rewrite the confidence interval formula here for you guys. Okay, it is the confidence interval, the two proportion Z interval is, it's P1 hat minus P2 hat plus or minus that margin of error, which is Z star times the square root of, and we've already got the standard error, but I'll go ahead and fill it in. P2 hat 1 minus P2 hat over N2. All right, that's our formula. Now, remember, we've already got the standard error, so that takes care of the square root. We know P1 hat, we know P2 hat. Only thing that we need now is Z star, and I'm hoping you guys are super familiar with how to do this now. But I will do it one more time. We want to be 95% confident, so we know the drill. Because we have all our conditions for the sampling distribution, we are approximately normal. Right down the middle is where Z is equal to 0. These are all Z scores. We have a negative Z critical and we have a positive Z critical. And the area between those two is precisely our confidence level, which means there is 5% that's not shaded. Divide that by 2 and we get 0.025, and for that same reasoning we get a 0.025 over here. Okay, so now we're going to go to our calculator, or we're actually going to go to StatCrunch. Okay, we go to, get my mouse over here. Remember, we go to Stat, we go to Calculators, and we're going to the normal distribution. Let me see, make it nice and big for you folks. All right, our mean is 0, our standard deviation is 1 because we're dealing with the standard normal distribution. We don't know the Z-scores, what we're trying to find, but we know the area to the left, we want that to be a 0.025. So we type that in, we compute it, and we get the familiar negative 1.96. Which means the Z critical that we're going to use is a positive 1.96. Always use the positive version. All right, so we have everything that we need. So here we go. The confidence interval will be, it's going to be P1 hat. If you remember, P1 hat was 0.23. So it's going to be 0.23 minus 0.19, that was our P2 hat, plus or minus Z star, which was 1.96, times, let's give ourselves a little bit of space here, times our standard error, which we said was a 0.017 from the previous part. Okay, so what's our confidence interval? It's going to be, so if I take 0.23 minus 0.19, that's a 0.04, plus or minus, let's go to our calculator, 1.96 times 0.017. To 3 decimal places, 0.033. And then next we add and subtract. Or let's subtract first. So we take a 0.04 minus 0.033. That's a 0.007. And if we add them, we're going to get plus 0.033. We should get a 0.073. Alrighty, folks, that is our confidence interval. Once again, I know it's a lot of work by hand. I'm going to show you how to do it in just a few minutes using technology. All right, interpret the 95% confidence interval. This is nothing new, right? We know the script. We are 95% confident that P1, so what was P1, right? And notice all of these are positive, right? So that means that P1 is higher than P2, so that we know that we are 95% confident that the population proportion, let's be clear here, the population proportion of college-educated adults is between 0.007 and what was the other value? 0.073 points higher than non-college educated adults. Okay, once again, why can we say that it's higher? Because, well, the confidence interval contains all positive values. Remember we said, let's go all the way back. Remember we said when the confidence interval contains all positive values, that means that P1 is higher than P2. Okay? All right. Let's go here. So a journalist claimed that the college-educated adults were more likely to order groceries online than non-college-educated adults. What does your confidence interval suggest about this statement? Well, remember, our confidence interval contained all positive values. And so that indicates that P1 is higher than P2. So that means that college-educated is higher than non-college-educated. So what does our confidence interval suggest about this? Well, our confidence interval seems to support this claim, right? We seem to agree with the journalists because, once again, all of our values in our confidence interval are positive. Okay, all right, this is what you really came for. All right, so now we're ready to do this confidence interval using technology, specifically StatCrunch. So the beautiful thing about using StatCrunch or technology, you only need a few things in order to calculate all of those values that we just did, the standard error and all that stuff. So all we need is X1, which represents, I like to use X1 to represent successes from sample 1. Okay, we need X1, we need N1. N1 is our sample size. And then we need the same thing for X2. Remember, X2 is going to be now successes from sample 2. And then we need an N2. All right, the beautiful thing is that we've already calculated those whenever we did our check on successes and failures. Remember that check at the very beginning, part A? So I'm just going to grab those values. Remember, let me get rid of some of these here. Remember, N1 times P1 hat tells us the number of successes in sample 1. So 621, that's the number of successes in sample 1. So we have 621 as our successes for sample 1, 2698 as the sample size. So let's go down here. X1, 621, N1, 2698. Let's grab the values for the second sample. What were those number of successes? N2 times P2 hat, that's a 133. And our sample size was 696. So 133 and 696. All right, once again, remember, sometimes these X values, the successes are given to you directly. Then you could just go straight to the calculator. But this time we had to figure out what those successes were. All right, once we have those values, we're ready to plug them into StatCrunch. So this is what you do. We're now in StatCrunch. We're going to go to, bring my mouse over. We're going to go to Stat. We're going to go to Proportion Stats. And we are going to go to sample this time with summary. Very important is with summary. All right, what we're going to do now is we're going to head over here, and it needs the number of successes for sample 1. That was 621. And our sample size for the first sample was 2698. Okay. The number of successes for sample 2, I believe that was 133. And that sample size was 696. Okay. All right. What are we performing? We're performing a confidence interval for P1 minus P2. Our confidence level is 0.95. Looks good. We click on compute. Drag this over. And look at that, boy. That is our confidence interval. I want to bring your attention to the standard error. Look at that. To 3 decimal places of 0.017. Exactly what we did by hand. And then our lower and upper limit of our bounds are very much in line with what we calculated. Once again, there's going to be a little bit of difference because of rounding and because of the fact that, remember, we had to round the counts. But yeah, look at that. To 3 decimal places, we have a 0.006 up to a 0.072. And if we compare that to what we did by hand, very, very, very close. Once again, we're off a little bit by rounding, okay? All right, listen, I want you guys to use technology. Nobody is going to ask you to do these things by hand, okay? So use technology. It gives us a standard error, and it gives us a quick way of getting that confidence interval. All right, guys, I appreciate you all, and I look forward to seeing you all in the very next video. Take care.